Welcome to today's paper reading. Today's paper is titled, The Unreasonable Effectiveness of Easy Training Data for Hard Tasks. This paper was published on the AR14 preprint by Peter Hase and colleagues from the Allen Institute for AI and UNC Chapel Hill. The abstract addresses the scalable oversight problem, which concerns training models to perform well on hard test data when hard training data is difficult to label correctly. As language models improve, this issue has gained more attention. The paper reveals that current pre-trained language models often generalize well from easy to hard data, sometimes performing as well as models fine-tuned on hard data. This generalization is demonstrated using simple fine-tuning methods such as in-context learning, linear classifier heads, and QLoRA across various measures of data hardness. The study also suggests that collecting easy data for fine-tuning can be more effective than hard data due to the noise and cost associated with hard data. The experiments involve models up to 70 billion parameters and datasets with varying question difficulties, concluding that easy-to-hard generalization in language models is robust for the tasks examined. The challenge of supervising language models, LMs, in specialized domains is significant due to the difficulty in correctly labeling data. This difficulty is reflected in both the time and costs required to annotate data, as well as the presence of label noise. When specific expertise is needed, the labeling difficulty becomes even more severe. For instance, even PhD holders can make errors on up to 40% of objective problems in specialized fields like physics. As NLP benchmarks increasingly focus on domain-specific tasks, obtaining large human-labeled training corpora may become infeasible. This leads to the question of how to train models to solve hard problems when labeling enough hard data for training is challenging. This issue is an example of the scalable oversight problem, which involves providing a good reward signal to a model when it is difficult to assess if its outputs are correct. In this paper, the authors studied the problem of easy-to-hard generalization, which refers to model performance on hard test data when fine-tuned only on easy training data, defined according to some human hardness measure. Figure 1 illustrates the performance of a Mixtral 8x7b model when prompted with easy data, such as third-grade problems, and its effectiveness on a hard task, like college problems. The results are shown for k equals 10 prompt examples, with performance averaged over 5 random seeds. The figure demonstrates that the model prompted with easy data performs almost as well on the hard task as a model prompted with hard data, indicated by the college bar. Figure 2 illustrates the effectiveness of supervising the Llama 2-70B model with easy data to enable generalization to hard data. On the left, the model is shown to generalize from high school-level computer science problems to a college-level computer science problem. On the right, it demonstrates the ability to handle math problems with 2 to 3 reasoning steps and generalize to problems involving 8 reasoning steps. The prompts used for this supervision are omitted for brevity. In the realm of curriculum learning, previous studies have concentrated on improving model performance on difficult data points by initially learning from easier data. This approach is believed to facilitate the learning of more complex concepts. Our research, however, focuses on examining how well models can generalize to hard data based on the difficulty of the training data. Our findings indicate that pre-trained language models, LMs, can surprisingly generalize well from easy to hard data, potentially reducing the need for meticulously designed training curricula. Compositional generalization research has demonstrated that neural networks often struggle to generalize to problems requiring the combination of reasoning steps not explicitly encountered during training. Recent work has begun to characterize the conditions under which models can generalize to more compositionally challenging problems. For instance, transformers have been shown to generalize better on algorithmic problems that can be solved using RASP, where the solutions can be implemented directly through a transformer forward pass. Additionally, recurrent test time computation has been found to be valuable for generalizing to problems requiring more reasoning steps than those seen during training. Our study aligns with these findings, showing that easy-to-hard performance on compositional reasoning problems can be surprisingly good compared to unsupervised-to-hard and hard-to-hard bounds. Easy-to-hard generalization has been motivated by the scalable oversight problem, which highlights the challenge of providing an appropriate reward signal to a model when it is difficult to assess the correctness of its outputs. Assessing easy-to-hard generalization provides valuable context for understanding the difficulty of this problem, as it informs us about how models might generalize from settings where they can be properly supervised to ones where they cannot. Past work in NLP has evaluated easy-to-hard generalization using model-based hardness measures and the number of compositional reasoning steps required to solve a problem. Our research extends this by using a greater number of human hardness measures, multiple datasets, and multiple model sizes to study scaling trends. We also show that in several settings, easy-to-hard generalization is comparable to hard-to-hard generalization. Concurrent work by Burns et al., 2023, explores a related weak-to-strong generalization problem, where a stronger model is fine-tuned using labels from a weaker model. In contrast, our study defines its main performance metric using an unsupervised model as the baseline, incorporates human hardness measures, and utilizes publicly available datasets and open-source models. The paper introduces several criteria to measure data point hardness, focusing on human-centric and model-based metrics. Human-centric criteria include education/grade level, which assesses the educational level required to answer a question, and expert rating, which gauges the difficulty from an expert's perspective using an ordinal scale. Another key criterion is required cognitive skill, which rates the cognitive complexity based on Bloom's taxonomy. Quantitative measures such as question number of words and answer number of characters provide proxies for question complexity. Compositional steps, which count the number of reasoning steps needed, also contribute to the hardness assessment. Additionally, the paper employs a model-based metric, minimum description length, MDL, which measures data point loss under a model family. MDL is computed by averaging label probabilities across models fine-tuned on increasing training data. This metric helps evaluate how well a model generalizes to hard data, simulating scenarios where human labeling is insufficient. Table 1 outlines the specific hardness measures utilized for each dataset in the study. These measures include education/grade level, expert rating, required cognitive skills, question length, answer length, and the number of reasoning steps. The measures are designed to capture various aspects of data hardness, such as the complexity of the questions and the cognitive skills needed to answer them. The table also indicates which measures are not available in the dataset's annotations and thus are not used in the experiments. In this experiment setup, the authors utilized several models including the Llama 2 70B base model, Llama 2 7B and 13B, and an RLHF version of Llama 2-70B. For data hardness stratification, datasets are separated into easy and hard categories using automatic cutoffs at the 30th and 70th percentiles, with manual cutoffs defined for specific datasets like ARC and MLU. The fine-tuning methods employed include in-context learning, ICL, linear classifiers trained on frozen model hidden states, and QLoRA with the LoRa implementation from Hugging Face PEFT. Figure 3 illustrates the relationship between accuracy and test data hardness across various datasets, utilizing Llama 2-70B with in-context learning, ICL. The data demonstrates that the difficulty levels perceived by humans are also challenging for language models, LMs. The error bars, representing 95% confidence intervals, CIs, indicate the variance in test sample performance. This figure underscores that as data becomes harder for humans to understand, it similarly becomes more difficult for LMs to accurately process and interpret. In RQ1, the authors explore how to measure data hardness. They validate the measures by assessing model performance across different hardness levels and create correlation heat maps. The results show that model accuracy declines for harder test data, indicating the measures capture meaningful aspects of data hardness. For RQ2, the focus is on whether models can generalize well from easy training data to hard test data. The results show that Llama 2-70B with ICL generalizes comparably to hard test data regardless of training data hardness, with a supervision gap recovered between 70% and 100%. In RQ3, the authors examine the cost-benefit trade-offs of collecting easy versus hard training data. They test under budget and noise assumptions, finding that easy data can be preferable due to lower cost and less noise, leading to better hard test performance. Figure 4 illustrates the accuracy of Llama 2-70B with in-context learning, ICL, on hard test data relative to the hardness of the training data, averaged over 5 seeds. The models demonstrate the ability to recover 70 to 100% of the supervision gap when fine-tuned on easy data. This suggests that the model can effectively generalize from easy training data to hard test data, regardless of the training data's hardness. Figure 6 illustrates the cost-benefit trade-offs between collecting and fine-tuning on easy versus hard training data. It shows that when hard data has noisier labels compared to easy data, fine-tuning on easy data can result in better performance on hard test data. This is demonstrated using the MMLU STEM 5 dataset with the Llama 2-70B model and a linear probe. The figure highlights that easy data can be more beneficial due to its lower noise levels, even though hard data might be more informative. Figure 5 illustrates that hard test accuracy tends to be higher when training on comparable amounts, costs, of easy data rather than hard data. This is under the assumption that hard data is twice as costly to collect. The results presented are for the Llama 2-70B model using linear probes. This suggests that, despite the cost differential, easy data can yield better performance on hard tests. Figure 7 illustrates that the performance on hard test data may start to decline when the model is fine-tuned on very easy data. This phenomenon is demonstrated using college-level STEM questions evaluated with the Llama 2-70B model. The decline in performance is particularly noticeable when the gap between the training data hardness and the test data hardness becomes significant. This suggests that while easy data can be effective for training, it may not always generalize well to harder test scenarios. In this discussion, we explore the implications of our findings regarding the difficulty of tasks for language models, LMs. We examine the largest difficulty gap tested, which spans from third grade to college-level STEM questions. This gap is relevant for future research that may define easy and hard tasks differently. We also discuss how LMs solve hard problems using as few as 10 easy examples. Our results indicate that fine-tuning on even small amounts of easy data successfully elicits relevant knowledge from LMs, largely invariant to the hardness of the data. This suggests that such fine-tuning encourages models to answer questions based on truthfulness representations of text, which should be consistent across different domains and data hardness levels. We emphasize that our results do not suggest that models are merely learning the task format, but rather show true generalization. We fit models using in-context learning, ICL, prompts that are simple but match the task format for MMLU and strategy QA, and find that model performance varies based on the hardness of the prompt data, not just the task format. This indicates that fitting to easy data encourages models to provide correct outputs for hard questions. In this study, the authors investigated the problem of easy-to-hard generalization. They found that several human and model-based hardness measures do not agree on which data is the hardest. Additionally, language models trained on easy data often perform nearly as well as those trained on hard data, recovering 70 to 100% of the supervision gap. Practically, it is better to collect and train on easy data when hard data is noisier or costlier to collect. The study also noted that the scalable generalization ratio may decline when the gap between train and test hardness becomes large. These results are robust across various datasets, training methods, hardness measures, and model sizes. However, the study is limited to datasets where humans can reliably label data and cannot verify if test questions are not in the training datasets of open models. There are also ethical concerns regarding the dual use of models in niche domains and the potential displacement of human labor. Thank you for watching.